Now we're going to talk about logarithm identities. When a logarithm looks in the mirror, this is what it sees. All of these things we're going to talk about right now. I have got four general identities. I would encourage you to jot these four down, and I'm just going to give you an example of them. Our first identity is log base b of b equals 1. And so, for example, if I were to write down log base 4 of 4, that will equal 1. If I were to write down another example of log base 3 of 3, that should equal 1. And if you don't believe me, convert it into exponential form. 3 to the first power equals 1. And really, this is always true because anything raised to the first power equals the anything. Also, another example, log base b of 1 will equal 0. It does not matter the base. As long as, I should say, in all these examples, b is not equal to 0, nor is b equal to 1. Any of these things, or maybe I could say that b is not equal to 1 and that b is greater than 0. So I suppose I could have a fraction as a base. But all these restrictions apply to these four properties here. So anyways, back to log base b of 1. Log base b of 1 equals 0, and you could see an example of that. Log base 10 of 1 equals 0, since 10 to the 0 power equals 1. Or let's go fancy here. Log base pi of 1 equals 0, since pi to the 0 power equals 1. Anything to the 0 power equals 1. And then here's another couple of strange ones. Log base b of b to the x equals x. And what that might look like is if I have a log base 2 of 2 to the 5th power, that's just going to equal 5. And again, you can kind of plug this in to exponential form and see what that looks like. This becomes 2 to the 5th equals 2 to the 5th, so that works. That's kind of like in the last example where you saw log base a of a squared. That came out to be just 2. So same type of principle here. Then we have this other inverse log property where if I take some exponent, or if I take a base and raise it to a log with the same base, it's almost like it inverts itself and almost like it cancels out. And so we get this x left over. So if I had 3 to the log base 3 of 4, that's just going to equal 4. And you can actually rewrite this in logarithmic form. If this is my base and this is or this is my exponent, this is my base, I could write this as log base 3. Actually, let me go another color here. I could rewrite this exponent as, well, let's stay blue. Log base 3 of 4 equals the exponent, which is log base 3 of 4. So this is just an identity. It's something that's always true. Sometimes it'll be useful to know these things. So that's why we kind of lead off with these. Next up, first property of log that we're going to talk about is multiplication. So if you think about the properties of exponents, they're going to tie in with the properties of the logarithms since they are inverses of each other. So first off, I want to start off with a property of exponent that if I have some 2 to the 3rd power and I multiply it by some 2 to the 2nd power, that should equal 2 to the 5th power. And really, remember, the property is that you add the exponents. So what I'm interested in here is I want to translate this into a property of logs that kind of involves the same type of mechanics going on with the math. And if you think about what's going on here, I kind of want to highlight just these exponents. What I want to do, because remember logs, that when you evaluate a log, it equals the exponent. So what I'd like to do is I want to kind of just focus on the exponents. In this case, 3 plus 2 equals 5. That's what's going on in the exponents of these powers here. So what I'm going to do is I'm going to actually kind of convert these using the same base of 2 into logarithms. So what I'll do is I'll say that this becomes 3 becomes log base 2 of 8. 2 becomes log base 2 of 4. And that should equal 5 becomes log base 2 of 32. Now that might seem a little bit like magic what I just did, but convince yourself that this is true. If I take log base 2 of 8, I'm thinking 2 to the what power equals 8, and all I've done is I've rewritten 3, 2, and 5 as just a log with a base of 2. Now what we're trying to do here is we're trying to find some patterns or some generalizations that we can make with these numbers. Well, what I notice here is that I can use an 8 and a 4 to get me to 32. And what that means is I can rewrite this as log base 2 of, and the way I can use 8 and 4 to get 32 is by multiplying them together. So what I've done here, again, it kind of looks like magic, but what I'm doing is I'm combining 8 and 4 and I'm multiplying them together to get me this 32. So it turns out that log, and you can see that 8 times 4 is 32, so log base 2 of 32 definitely equals log base 2 of 32. And really what the magic is when I combined using this addition, when I'm adding these logs together, it becomes a one log where I multiply the inputs together. So here we added the exponents, and when we're multiplying with the same base, we add the exponents. Here, if we are adding logs, we multiply the inputs. So that's kind of the generalization that we're doing here. We could see another example, just for the sake of example, and let's do one with other numbers. Let's say I'm going to take 3 to the first times 3 to the third, and that should equal 3 to the fourth. And once again, we just add these exponents. So if I were to write this just as some addition problem, I would have 1 plus 3 equals 4. And I can rewrite these as logs. I could say log base 3 of 3, that's equal to 1, plus log base 3 of 27, that's equal to 3, equals log base 3 of 81. That's equal to 4. And what you might know or notice is that if I multiply 3 times 27, it's a multiplication sign, I do get 81. So log base 3 of 3 times 27 should equal log base 3 of 81. So to generalize this, let me just put it one big rubber stamp on this and say this is our property of logs. This is a rule. Let's put this in blue here. Here's my general log property. If I have some log base b of m plus some log base b of n, that is equal to 1 log, same base, of the product m times n. So I can use this generalization to either combine logs into one as long as I'm adding them with the same base, or I could take one log that has a product and I can expand them and make them a sum. All right, so that's our first property of logs, multiplication. Let's talk about division next. And just like I did before, let's start off with some numbers that we're familiar with. If I were to take, let's say, here, what do I want to do here? Let's say 2 to the 5th, over 2 to the 3rd, that's equal to 2 to the 2nd. So the property that we're talking about here is when we are dividing with the same base, the property is you subtract the exponents. And so once again, just like I did before, I want to focus on these exponents. I want to focus on the 5, I want to focus on the 3, and I want to focus on the 2. I want to subtract exponents. So that means I'm going to be subtracting logs, since logs evaluate to be these exponents. So I want to create some sort of an expression or an equation with what I've just done here. 5 minus 3 equals 2. And then just like I did before, I want to convert these into logs. So 5 is going to be log base 2 of 32 minus, and this will be log base 2 of 8, and that should equal log base 2 of 4. And once again, if you need to pause the video to kind of make sense of what I just did here, please do so. I just converted 5 into a log with a base of 2. Now when we are looking for patterns or generalizations we can make, well, I noticed that I can use 32 and I can use 8 to get me to 4 by taking the quotient of those two things. Log base 2 of 32 over 8 is going to equal log base 2 of 4. So in fact, when I divide 32 by 8, I get 4. These two things are equivalent. So kind of the magic that happened here is I took this subtraction and I turned it into a quotient. So again, what I've done here is I'm kind of starting with the exponents. I'm taking the exponents, I'm making them into logs, and I'm finding some generalizations or things I can do with these things. So before, when we were dividing with the same base, we subtracted the exponents. Now we're talking about logs, we're inverting this whole process. So if I am subtracting logs with the same base, I take the quotient of the inputs. So this is exactly the same as what we already know with exponent properties, but it's flipped, it's inverted. So in general, let's just skip another example. Let me just give you the generalization here. If I have log base b of m minus log base b of n, that's going to equal log base b of the quotient m over n. You can go both directions with this. I can go from here to here or from here to here. All right, one more property I want to talk about, and that is the power of powers. Let's take an example, 2 squared to the third power, and we know that's equal to 2 to the sixth. And our rule here is when we are a power to a power of same base, what we do is we multiply the exponents. And so once again, I want to focus on the exponents and convert this into logs. So I want to focus on the 2, on the 3, and on the 6. Now this one's going to look a little bit different because what I'm actually going to do here is think about the reason why we multiply 2 times 3. And it's because I'm taking this whole quantity, 2 squared, and I'm multiplying it by itself 3 times. So I have 3 groups of these things. So what I'm going to do is I'm going to write this as 3 times 2 equals 6. I want 3 groups of these 2 squareds. And I'm actually going to switch things up a little bit, and I'm not going to convert all of these numbers to logs, but I'm going to actually convert just 2 of these numbers to logs. So I'm going to keep the 3 as a 3 for now. And this is going to be multiplied by, I do want to convert this to a log, so this will be log base 2 of 4, and that's going to equal log base 2 of 64. All right, so let's see what I've done here is I've written 3 times log base 2 of 4 equals log base 2 of 64, and that should be true. Since this is equal to 2, 3 times 2 is equal to this, which is equal to 6, since 2 to the 6th is 64. Now, where is this helpful? Where is the property hiding in this? I can rewrite, if I wanted to use a 4 and a 3 somehow together to make 64, I can do that by actually raising 4 to the third power. So what I've done here is I've actually taken this 3 and I've almost like moved it into the input where I'm raising that 4 to the third power. So now what I'm doing here is what I've taken, I'm multiplying a constant by a log, and that becomes the exponent of my input. So this one's a little bit weirder than the other two because it's not immediately apparent where it comes from. But hopefully by seeing this example with numbers, we can get that generalization. So in general, if I have some log base b of m to the a power, that's going to equal a times log base b of m. All right, so that's my power of powers. Those are the 3 big ones. And let's see some examples of this. Let's now put them into practice. I want to use my laws of logarithms to combine all this into one log and simplify if possible. So over here I have a sum between these 2 logs, so I'm going to multiply. I'm going to use the multiplication property. So this becomes log of 5 times 3, which is equal to the log of 15. All right, that's one. That was easy. Now let's take this example here. I'm subtracting them, so that's going to be my quotient property. So this is going to be log base 3 of 24 over 8. And this is where we want to simplify if possible. This is going to be log base 3 of, I do know what 24 over 8 is, that's 3. So in fact, this whole expression here equals 1. Next up, I've got this one here. This is log base 5 of 25 to the third power. This is going to be my power property. So I'm going to take this 3 and move it to the front of my log and multiply 3 times log base 5 of 25. I know that log base 5 of 25 is 2, so this is 3 times 2. So this whole thing actually evaluates to 6. And our final example here, I have a couple things going on. I have subtraction and I have the power to a power. Now, one thing that's important is the order in which we do this. So because I have a subtraction, I might want to think that I want to go to the quotient, but you can only use that quotient property when, let's back up a couple slides, when I just have a log by itself and a log by itself. Notice there's nothing in front of either of these logs. I don't have a constant. This isn't 2 log base b of m. So what I need to do is I need to make this into looking like just a log with one input. So that means I'm going to first start off by taking my power property and convert these into log base 7 of 2 minus log of 2 cubed. And I think I just did base 7, but this is base 10. So this is log of 7 squared minus log of 2 cubed. So this is where things get confusing, because even as I misspoke, we have to be careful of our terminology and how we write things. This is much different between, or this is not the same thing as log base 7 of 2. These are not the same, not even a bit. So be careful to make that distinction. This is what I have written up top here is log base 10 of 7 squared. But anyways, now that I've gotten this down to a log of one thing minus a log of one thing, I can rewrite this using my quotient property and say this is log base 10 of 7 squared over 2 cubed. And I don't think that I can simplify this any further, so that one's done. All right, lots of stuff we've done here. Why don't you try these 4 examples on your own, pause the video, and see how it goes. And here are my answers to these 4 problems. Hopefully it went all right for you.